So good morning dear students, welcome to my physical chemistry class. Okay, today I wish to take the electrochemistry. So the 6th semester physical chemistry, that is physical chemistry 3, consists of various topics. The main part is electrochemistry. Okay. So first we have to discuss that part, that is electrochemistry. After that we have to discuss the solution, then solid state part 1 and 2, etc. So as you know that electrochemistry is the branch of chemistry that deals with the interaction between the electricity or electrical energy and chemical energy, or vice versa. Okay, both aspects comes under the electrochemistry. So the term electrochemistry deals with the interaction between the electrical energy and the chemical energy, and thus it deals with the transformation between the electrical energy into chemical energy or the chemical energy into electrical energy. Okay. The first part, that is the electrochemistry that deals with the transformation of electrical energy into chemical energy, is actually discussed under the heading called electrolytic conductance. And the second part, that is the transformation of chemical energy into electrical energy, is dealt under the heading called EMF. Thus, electrochemistry has two different parts or two different aspects. One is the electrolytic conductance on one hand, and the other is the electromotive force or EMF on the other hand. So first you have to discuss about the electrolytic conductance. So electrochemistry. Chemistry that deals with, deals with the interaction of electrical energy and chemical energy. It actually involves, involves the transformation of electrical energy into chemical energy, and two, the transformation of chemical energy into electrical energy. Okay. The first aspect, the transformation that deals with the branch of electrochemistry that deals with the transformation of electrical energy into chemical energy comes under the heading called the former. The former part is discussed under the heading, under the topic or heading called electrolytic conductance. Electrolytic conductance. So here we discusses the molar conductivity, equivalent conductivity, then that is Faraday's laws, etc., and certain other theories of electrolytic conductance. That is Collas's theory, Arrhenius theory, Collas's theory, Oswald theory, and it comes up to that goes up to the famous De-Becquerel theory of electrolytic conductance. All are discussing, and method for determination of transport number. All these are discussed under the heading called electrolytic conductance. And the latter aspect, the latter part or second part, that is the transformation of chemical energy into electrical energy. The latter part is discussed under the heading called EMF, that is electromotive force of galvanic cell. So what I wish to mention here is that the electrochemistry, the discussion of electrochemistry is mainly classified into two aspects or two branches. One is the electrolytic conductance, which deals with the transformation of electrical energy into chemical energy, that is bring about in chemical system, and the related properties in connection with the conductance. And the second aspect, that is the transformation of chemical energy into electrical energy, is discussed under the heading called electromotive force, where we are to go discussing the various non-stication, the thermodynamics of galvanic cell, various types of galvanic cell, concentrated cell, etc. And also the fuel cell. All these are discussed, and the application of EMF. All these are discussed under the heading called the EMF. Okay. So first part we have to discuss is the electrolytic conductance. There is the electrolytic conductance. So we have discussed about this. Okay, we can discuss in detail the electrolytic conductance in detail. So first of all, we have to know what are an electrolytic conductor or electrolyte. Okay. Conductance are mainly classified into two. One is the electronic or metallic conductor, and second is the electrolytic conductors. So conductors, that is any substance. Conductors are, as you know, is any substance that can pass electricity through it or allow the passage of electricity through it are called conductors, or generally called good conductors. All others are called insulators. Those substances which do not allow the passage of electricity through are called insulators, while those substances which allow the passage of electricity through it are called conductors, electrical conductors, and in between these two still there is the semiconductors. Well, thus we are discussing about the conductors, those substances which can allow or pass electricity through it is called conductors. The conductors are of two types. Conductors are of two types. One is the metallic metallic conductor, and second is one metallic conductor and two is electrolytic conductor. Okay. What is a metallic conductor generally? Any substance that allow the passage of electricity without any chemical change are called metallic conductors. Okay. All the metals and metallic alloys and graphite comes under this group. One of the non-metal graphite also a good conductor. So metallic conductors, that substances allow the passage of electricity without any chemical change. Okay, they simply allow the passage of electricity. All the metals comes under this category and they are usually called metallic conductors. While the electrolytic conductors, simply called electrolytes, are those substances which allow the passage of electricity through it with chemical change. Okay, any substance which allow the passage of electricity through it with chemical change or chemical decomposition are called electrolytes or electrolytic conductors. All the ionic substances in their molten state or in the solution, aqueous solution states are good electrolytic conductors. So all the ionic compounds, the solution of aqueous solution of our ionic compounds are called behaves are electrolytic conductors or in their molten state. Then we have to look into who is responsible for this conducting electricity. The case of metallic conductors, how they have become conductive. In the case of metallic conductors, the free electron present in the metal or alloy, the free electron present in the system or the material conduct electricity or they allow the passage of electricity through it, or they act as the carriers of electricity, hence they are called electronic conductors. So in the case of metallic conductors, the electricity is carried by the free electron present in the system, hence they are called electronic conductors. Free electrons are the carriers. Free electrons. Hence they are called electronic conductors. Electronic conductors. While in the case of electrolytic conductors, the free ions, the positive ions and the negative ion, free positive and negative ion present in the solution or the molten state carry electricity, or they make them conductive, and hence they are called ionic conductors. So since ion acting as the carriers of electricity, they are called ionic conductors because the free ions are the carriers. Free ions. Free ions mean positive ions and negative ions. The positive ion, cation, and negative ion. Anions are the carriers of electricity, hence they are called ionic conductors. So electrolytic conductors are ionic conductors, while metallic conductors are electronic conductors. In chemistry, we are actually dealing with the conductance in electrolytes, or we are actually dealing with the ionic conductors. Okay, but in physics, in connection with the Ohm's law, all these are discussed in the case of metallic conductors. So these are the main distinction. That is, those substances which allow the passage of electricity without any chemical change, they are called metallic conductors, and they are the carriers of electricity. They have free electron present in them, and hence they are called electronic conductors. While in the case of electrolytic conductors, that is those substances which allow the passage of electricity with chemical change are called electrolytic conductors, and that process is called electrolysis. So, okay, the process by which a substance undergoing chemical change by the passage of electricity, that process is called, that chemical decomposition is usually termed as electrolysis, and therefore such conductors are called electrolytic conductors. Actually, chemical change occurs. So here the carriers are both the free positive and negative ion present in their aqueous system. All the ionic compound in the aqueous state or the molten state acting as the electrolytic conductors. So here the carriers are free ions, and hence they are called ionic conductors. And second is the case of the influence of temperature. That is, the temperature has a profound influence, remarkable influence in the case of both the cases. That is the case of metallic conductors. As the temperature increases, the conductivity gradually diminishes, slowly diminishes. Okay. But in the case of electrolytic conductors, as the temperature increases, its conductivity increases. Okay, it is easy to explain. The case of metallic conductors, as the temperature increases, the thermal vibronic motion of the nucleus increases, or oscillation of the nucleus increases. The thermal vibration or the oscillation, vibronic oscillation of the nuclei increases. Therefore, it offers a sort of blockage or a sort of block to the, or hindering to the free movement of the electron through it, through the metallic lattice. You know that as the electron are moving from towards a particular direction, what is actually happening is that as the temperature increases, the positive core of the nucleus, that is oscillation, it vibrates the greater amplitude, and it offers a sort of blockage, okay, to the free movement of the electron, and that by the resistance increases, conductivity decreases gradually with the increase of temperature in the case of metallic conductors. But in the case of electrolytic conductors, as the temperature increases, more and more ion, the degree of dissociation of the electrolyte increases, more and more ion get free, and also the mobility, the ionic speed of the ion increases with the increase of temperature. That may also the another aspect. Okay, so what you expected in the case is that as the temperature increases, the degree of more and more free ions are produced, and also the speed of the ion increases, and it is generally speculated that as the temperature increases, the conductance of the electrolytic conductance increases. But in the case of metallic conductor, it diminishes. Okay. The next is the effect of dilution. That's also very important. The case of electrolytic conductors, as you know that the metallic conductors, they are usually metals, either in the form of a rod, rod or a block, etc. like that. So as we increases, here there is no such case of dilution in the case of metallic conductor, because the behavior of the conduction depends on the nature of the material. Okay. So as it becomes more and more less, that is about narrow. Okay. I mean, usually resistance decreases and conductivity increases. But the case of since we are dealing with the solution, aqueous solution of the ionic compound as the electrolytic conductors, dilution has a profound influence, because as the dilution increases, the speed of the ion increases, and hence the conductance increases. So that is the case. So this has to distinguish between. So example, we are all metal and metallic alloy, and a non-metal called the graphite. The case of electrolytic conductors, all the ionic compound in the aqueous solution acting as the electrolytic conductors. In the case of metal, free electron are carriers. Here the free ions are the carriers. So they are called electronic conductors. The second are called ionic conductors. The case of metallic conductors, as the temperature increases, conductivity decreases. The case of ionic conductors, the conductivity increases with the increase of temperature. So let's try to pass on to the conductivity in electrolytic conductors, conductance of the electrolyte. Okay, before that, we have to pass on to the general rule governing, the quantitative rule governing the electrolytic conductance. That is, when we pass a definite quantity of electricity through any of the electrolytic substances or electrolytic conductors, it undergoes chemical change, thereby it get destroyed. The substance get destroyed actually, or it get exhausted. The chemical species get exhausted, or it undergoing chemical change. How much chemical change? The amount of chemical decomposition can be easily quantitatively expressed by means of a theory or rule that is called Collat's law. That is the Faraday's laws. It's very simple. These all are elementary idea. The law, the quantitative law that is governing the relation between the amount of chemical change and the amount of electricity. Okay, the quantity of electricity and the amount of chemical change that is related by the Faraday's laws. There are two laws. One is first law and second. There is second law. Okay, you have to remember. Faraday's laws of electrolysis gives the quantitative relationship between the quantity of electricity passing through an electrolytic conductors and the amount of the chemical change that it is undergoing. So what is actually electrolysis? Electrolysis. The process of chemical decomposition that is carried out in any electrolytic conductors by passing electricity through it is called electrolysis. That is the general definition. The process by which any electrolyte conductance undergoing chemical change by the passage of electricity through is called electrolysis. Okay. And there is a quantitative relationship between the quantity of electricity and the amount of chemical change that is taking place in any chemical system. According to first law, that is expressed by Faraday's law. According to Faraday's first law. First law. First law. That is, it states that is, the mass of each substances deposited at each electrode is directly proportional to the quantity of electricity passing through the electrolyte. That is the first laws of Faraday's first law of electrolysis. The amount or weight, the amount M of any substance produced at any electrode is directly proportional to I, the quantity of electricity passing through it. Okay, where M is the mass of the substance deposited in gram, the weight, and I is the quantity of electricity in coulombs. Suppose, M is proportional to Q, where Q is the quantity of electricity passing through the electrolyte. Suppose I is the strength of the current passing for a time t, then Q is equal to IT. Q is equal to IT. Therefore, we can say M is equal to a constant Z into IT, where the constant Z is called the electrochemical equivalent characteristic of the substance that is deposited or produced. Okay. So we can do first law of electrolysis, we can say M is proportional to Q, or M is proportional to IT, or M is equal to Z into IT, where I is the strength of the current passing for a time t, second or minutes, through an electrolyte solution, or IT is the quantity of current Q, okay, in coulombs. And Z is called the electrochemical equivalent, ECE. So the characteristic constant, ECE of the substance. Okay. What is Z? That is when Q is equal to 1 coulombs, or I into I is 1 ampere, T 1 second. 1 second. Okay. So 1 ampere of current is passed for 1 second, or if the quantity of current is 1 coulomb, then M is equal to Z. That's the definition of Z. So the electrochemical equivalent of any material is a standard quantity. Okay. It is defined as that quantity of the material that is deposited by passing exactly 1 coulomb of electricity through it. Well, it is exactly the amount of the substance that is produced by passing 1 ampere of current for 1 second. Both are correct. So, the electrochemical equivalent is that of a material, characteristic of the material, that is equal to the amount of a substance that is deposited by the passage of exactly 1 coulomb of electricity. So remember, the constant that we arrive from the first law of first law of Faraday law is Z, the electrochemical equivalent, is usually a very small quantity of the order of 0.000 something. So usually that the graph. So it is characteristic of the substance. Okay, that is equal to M. That is defined as M when Q is equal to 1 coulomb. And second law. The second law, Faraday's second law, it states that second law, if same quantity of current is passed through different electrolytes connected in series, then the amount of different substances deposited at different electrode or each electrode is directly proportional to the respective chemical equivalent. Okay, that is also very important. Faraday's second law states that if same quantity of current is passed through different electrolytes which are connected in series, then you know that suppose we are passing same quantity of current through 3 different types of electrolytes like K, potassium iodide, AgNO3, copper sulfate, etc. So that the different substances are deposited at each electrode. That is, on one hand potassium is deposited or hydrogen is deposited, whatever may be, on the other hand silver is deposited, on the other hand copper is deposited. All this happens depending on the condition. So the amount of each substances or different substances deposited in each case in different electrolyte is directly proportional to their respective chemical equivalent mass. Okay, that is in series, then the amount, the mass of each substance or different substance deposited is proportional to their respective equivalent mass. That is, M is proportional to E. M is proportional to E. Where M is the mass of the substance deposited and E is the equivalent weight of the material. For example, suppose we have, as I mentioned, we have AgNO3 electrolyte, and the other is a copper sulfate electrolyte here. Okay, and the other is any other potassium nitrate, KNO3 electrolyte connected in series. They are connected in series such that the same quantity of electricity is passing through the electrolyte. Then you know that here silver is deposited on the cathode, here copper is deposited, and here is potassium is deposited, okay, in the respective electrode. Then the amount of copper, a silver deposit is proportional to the equivalent mass of silver. The amount of copper deposit is proportional to the equivalent mass of copper. The amount of potassium deposit is proportional to the equivalent mass of potassium, provided the same quantity of current is produced. So we can write, that is, M1 is proportional to E1, M2 is proportional to E2, M3 is proportional to E3, or generally M is proportional to E, provided the same quantity of current is passed. So from the first law we got the relation, that is M1 is proportional to E1 and M2 is proportional to E2. If the quantity of this current is same, then we can write M1 by M2 is equal to E1 by E2, or M1 by E1 is a constant. M1 by E1 is a constant. So we can write M1 by E1 is equal to M2 by E2, or M1 by M2 is equal to E1 by E2. That is, we have to remember. So we can second law can be remember like this. That is, M1 by M2 is equal to E1 by E2, provided the quantity of current is same, or M1 by E1 or M1 by E1 is equal to M2 by E2. Okay. M1 by E1 is equal to M2 by E2. That is the second law. Then from the second law we can arrive, okay, to arrive to another constant that is called Faraday. That is the after effect of the second law. That you have remembered, M1 by E1 is a constant, okay, provided. You know that. Suppose you remember an argument like this. M1 is proportional to E1 and M2 is proportional to E2. Okay. It is proportional to E2. Provided the quantity of current is same. Okay. Suppose E1 and E2, the chemical equivalent weight of the substance produced are respectively their one equivalent. Okay, you know that? According to second law, we can argue that the mass of each substance deposited is proportional to their respective equivalent mass or equivalent weight if the same quantity of current is employed. On the other hand, or rightly, the quantity of current required to produce one equivalent mass of any material is always a constant. Okay. Therefore, we can write the quantity of current. Okay, argument. If M1 is proportional to E1, if it is one equivalent, then the quantity of current, you say like. Similarly, M2 is proportional to its respective equivalent, one equivalent. Then, if same quantity of current can produce that is proportional to their equivalent mass, we can say that a particular quantity of current can produce one equivalent of any substance. Okay, therefore the quantity of current required to produce one equivalent weight of any substance is always a constant. And that is called Faraday. And that is called Faraday F. That is equal to F 96,500 coulombs. That comes the right definition. Suppose the same quantity of current is passed through the different electrode, right? The amount of each substance deposited is proportional to their respective equivalent mass. Therefore, the quantity of current required to produce one equivalent mass of any substance is always a constant. And that constant quantity of current required to produce one equivalent mass of any material is called Faraday. That is equal to 96,500 coulombs. That is the definition. Or we can say, or the first law, we can write M is proportional to, okay, Z. M is proportional to Z. Okay, Z. Then According to the second law, M is proportional to E. M is proportional to E. Then you remember the quantity of current, first law. The quantity of current, you can write according to first law. That is, the quantity of current required to produce 1 gram equivalent, okay, 1 electrochemical equivalent, okay, now you have to remember, that is, what is the first law, that is Z, you know that, suppose Z is equal to M, Z is equal to M, okay, so much gram, if Q is equal to 1 coulomb, Z is equal to is 1 coulomb. So 1 coulomb of electricity, if 1 coulomb of electricity can produce how much gram? Z gram of the substance. Okay. 1 coulomb of electricity produce Z gram of the substance. Okay, according to this equation. Therefore, the quantity of current, so 1 gram of the substance, 1 gram of the substance is deposited by how much quantity of current? Okay, the quantity of current required to produce 1 gram of the substance is, you know that 1 coulomb of Z gram of the substance is produced by 1 coulomb of electricity. Therefore, 1 gram of the substance is deposited by 1 by Z coulomb. Okay, 1 gram of the substance is deposited by the amount of the quantity of current required to produce 1 gram of the substance is 1 by Z. Therefore, the quantity of current, you know that what is Faraday? It is the quantity of current required to produce E equivalent of the E gram of the substance. Quantity of current required to produce E gram. Okay, that is the one equivalent. E gram of the substance is 1 by Z into E. That is equal to F. So we have F is equal to E by Z. E by Z. That's our definition. Okay. So what is Faraday? Faraday is E by Z. That we got the definition like this. So what is Faraday? Faraday is the amount of the current required to produce, okay, 1 gram equivalent of any material. The quantity of current required to produce E gram of the substance is 1 by Z into E, that is equal to F. Okay. So we can stop now. Next we have to discuss various aspects of electrolytic conductance. Okay, the conductance represented by G, the specific conductor represented by kappa, then the electrolytic conductor, that is a molar conductance, connection with the concentration solution, that is lambda. All these are discussed later. Thank you very much. Okay, so I'm going to wind up the class, so we can continue the class later. Thank you very much.